completed. Okay, so today we have Maximilian Attems, who is going to talk about medium-enhanced gluon to CC bar production. So Maximilian is an expert in jet quenching and aerodynamics and hot QCD in general. So you did your PhD in Frankfurt, right?
In Vienna.
In Vienna, and then he has been in Barcelona, here at IGFAE, and he's now working at CERN. And we are very happy to have you here today. So when you want, you can start.
Thank you, Carlos, for the invitation. It's great to be back. I will discuss on behalf of this CERN collaboration a possible measurement of the medium-enhanced gluon to CC bar production. So first, allow me to give you a view of the biggest particle lab on Earth. So we are sitting at Merin on the Swiss-French border. You see the airport and the Rhone here to the left, and the Lac Léman. So the LHC is circumference of 27 kilometers is really massive. And for those who like to hike or to go winter skiing, Le Reculé-Girard offers great sight on all of the experimental points. So you have CMS just below when you go up to the Col de Fossil, and Ellis in Merin. It's a dream machine who follows this steps of science in reference of Goethe to understand what's most fundamental particles. So there's, of course, the big part is the heavy ion program at the Large Hadron Collider, and we have seen these discoveries at the LHC. So anisotropic flow, both not only the elliptic V2, but also triangular and quadrangular flow are by now measured by different experiments. Here I'm showing Ellis PL, and the measurements are in excellent agreement with hydrodynamics. Hence, we speak of the almost perfect fluid which is produced at the LHC. And then we have, of course, it connects to jets. We see that in heavy ion, the bigger the fireball is, the more central the collision, the more suppressed this inclusive measurement is to be seen. This is from Atlas, but this is across all experimental measurements. Of course, not everything is all good. While we see signs of collectivity in smaller systems, we have yet to find hints of jet quenching. Maybe it's just a question of probabilities that we haven't measured enough of them, or it hints deeper. In any case, what we have seen up to now is that the processes that lead to this the hydrodynamization and the transport coefficient of jet quenching hint that there's the same mechanism in the QGP formation. And the most successful phenomenological from the QCD side is the bottom-up scenario. And we see that nowadays many different scenarios can lead to the same hydrodynamization, to the same attractor. these are very different theories. So from strongly coupled holographic theories to extrapolated QCD kinetic theories. And then, of course, there's also development on the toolbox. So several groups worldwide push this Bayesian analysis of the heavy ion collision. Here's the example taken from our CERN theory group. So Wilke van der Schee has this trajectum code where he can use more than 500 data points and has different parameters in which he can describe then the lead and oxide and future oxygen collisions. And what's seen is that eta over S is really small. I mean, bulk viscosity is not yet constrained, but yeah, several hydroparameters who are be able to get a good range of validity for this groups. Now, allow me to recap what we know about heavy flavor production. So the mass range of the charm is much bigger as lambda QCD, and this removes many non-perturbative effects, which will allow us to use QCD calculation to predict heavy flavor. And there's experimental evidence that this cross section is very good in predicting the yield of the production of both bottom and charm quarks, and that the QGP only modifies the transverse momentum of these quarks. So here on the left, you have this comic picture of the medium, and then this gluon with a certain virtuality split into CC bars inside of the medium, and further. So we know that this heavy quarks rescatter inside the QGP, and we are looking for a specific process, long distance one, to where we have two collinear charms, because this way we can, depending on the energy of the gluon, will be able to probe the medium. And of course, this goes back to the seminal work done here by Santiago group, by Liliana, Carlos, Guillermo, and Gavin, where they used this top quark process to see to get to this thermometer to see how the distribution of the formation time depends on it. Of course, the top is quite massive, so this is for the future collider, which should be colliding at much higher energies. Here on the right, you have different curves for collision energies at 39, 20, or 11. But even maybe with enough luminosity, the Large Hadron Collider, one may also get already access. So this is the inspiration of the work to go to not the heaviest quark, but the ones who are around the Q hat L. Now allow me a side remark. There's an exciting LHC hybrid seminar next week. So this has just been published in Nature by Alice. The evidence of the experimental evidence of the QCD dead cone effect. And so this will be next Tuesday at 11. This is a hybrid LHC seminar. The press office made this very beautiful picture of the dead cone effect. And there's a contribution from former PhD and leading contribution from Laetitia, and speaking will be Nima Zaharov, who has been a key in reconstructing. So in this seminar you'll hear much more about D0 tagging and the current capabilities of Alice of the previous run to data. So yeah. Just closing this side remark on this exciting evidence from Alice, where we which is also related to D0 and where one sees that there are great experimental capabilities. Coming back to our work, we are interested in this long distance process because then the time of this splitting is bigger as the hard time, and you may have a splitting which is modified by the medium, and so we used BDMPS-Z way to calculate the splitting function, and it's an experimental signature for in production in high-speed jets. The idea is that one goes in PQCD and can factorize this thing. So this is only possible if the momenta addition of this charm and anti-charm Q squared is smaller than S hat. And so we select this specific splitting in the collinear limit, and then depending on the energy of the gluon, with a very small energy of the splitting would occur very early or during the QGP lifetime or later on. Depending on the gluon energy, we get this different traces and hope to see this modification. So this goes back to the short discussion we had in quark matter with Carlos. We have the energy of the gluon. And then we have a charm and anti-charm, and we assume a very basic brick. So the medium is specified with L with the medium length, and we find that we can use this dipole cross section and have this corrected Z dependence. So in the online archive, there's still not fully general version of this formula, which is only valid for z equals 0. We will shortly upload a corrected version. And the results shown today are for this Z dependence. And so this is just a side remark from this notes that we can use this dipole to compute the scattering amplitude. And we split the derivation in 3 different for early times, intermediate times, and late times. So this in the time ordered formalism, and we see that at early times there are no correction of order 1 over nc squared, and you have just an average of 2 Wilson lines. Also at intermediate times, the corrections do not complicate the structure, but for late times, the structure is more complicated, and if you would do full 1 over nc squared, then you would get the quadruples. So the dragons are inside of this so. So for earlier times and intermediate times, this formula is of the order of 1 over nc squared, but not for the late times. From the calculation, we now can get how the magnitude of this in medium modification, and we see also in comparison to model extraction in central lab data that we use a conservative range of Q hat L from 1 to 8 GeV, and
Maximilian, can I interrupt you 1 moment?
Yeah.
So what does your sorry?
Yeah.
So what does your splitting function depends on? In which variables? I mean, usually when people talk about a splitting function, you think of only the longitudinal fraction of the energy, but this depends on a transverse momentum also.
Right.
So how do you define that momentum?
So we have the position of the C and C bar in Y. And
no, I mean, in terms of observable quantities, I mean, it's the momentum of what? Is the momentum of one of the quarks? It's some combination of the momentum of the quark and the anti-quark? It's
the difference between them.
The difference. It's not weighted by z's in any way.
No, we do weight by z.
Okay.
In the bracket, is that the partial derivative over the both x dot partial derivative over both tau? I think that gives the transition.
No, but I mean, this. I think we can agree that this formula is wrong. I mean, you already have new formulas in the new notes that Urs sent me yesterday. I mean, here you have the broadening of only one of the quarks in the final region, which is not what you want to do. So this formula is it's a little misleading, I guess.
No, but you mean
no, I mean that exponential that appears at the end of the first line of the long formula. that exponential of the integral from y bar to infinity. That's the broadening of only one quark.
Right. Okay.
This expression is old one.
Yeah, you're right. This is a previous expression. Yes.
Yeah, but that's important because here in this formula, your Kc is conjugate to r, and r is the position of one of the. I mean, if Kc is really a relative momentum, then that broadening will not be correct. I mean, this is only that can only match in the z to 0 limit. And now you corrected that, and you have broadening on both legs, but that makes it you have to be more careful with what are your momentum variables at the final state.
Okay, no, I agree with you, Fabio. I'll have to correct this formula. I mean, what we have been using to compute is basically this was this one, is this multiple scattering amplitude.
Sure.
Which you have the nodes based on, right?
Yes. No, my concern is what you do, because I mean, you calculate something that is going to be differential in a lot of momentum variables, but you have to be careful what are the ones that you want to keep, what you want to fix, and what you want to integrate. That's what I mean.
Right. Yeah. I mean, this slide is consistent with the results shown below. So this formula is not consistent. I agree. I will not have time to go through the full derivation.
No, sure. No need to go to the full derivation, but I think it's important to specify what is the momentum that you're splitting depends on, and out of all the momenta involved in the process, which ones are integrated over and which ones are kept explicitly.
Okay. Yeah, I take your point. On the phenomenological extrapolation, we set Q hat L to be between 1 and 8 GeV as a conservative range, and so this means that it's approximately the squared of MC, and the medium modification has the same magnitude as a mass term, and this is known to give sizable effects. So what one gets out just of the simple argument is that the medium modification is likely to be relevant, and of course in the future one can think of more involved objects than the brick we will use for the splitting. So Kc is the relative transverse momentum of the pair, and increases of Kc squared due to transverse momentum broadening on the individual quarks. And so what is exciting, what one gets is that it enhances the gluon to CC bar splittings, and you get two effects. So you have gluons which could not split in the vacuum, now can split, because the vacuum, the medium allows them now. And there's an increase of conserved and traceable quantity via interaction of the medium. So this is of course this very specific process. It will not have a huge impact on the global charm quarks that you get process. But what we see is in the phase space. We see on the one hand this strong enhancement for Kc squared approximately of the order of Q hat L, and then on this side the depletion of low Kc squared splittings. This is due to the in medium broadening. And so this formalism that describes enhanced gluon radiation, the BDMPS, also predicts a sizable enhancement of the C/C radiation. So with Gian Michele, we have an experimentalist in our group, and so we were devising to look for an observable that Alice or the other experiments could maybe measure. And so the experimental strategy who will describe you is based on Pussier. So the idea is that you count. It's just a simple counting of the jets which have a D0 bar pair, a single pair inside, divided by the inclusive jets. So this gives you information about the gluon to CC bar splitting, and it should be accessible down to low transverse momentum in heavy ion collision. And with this calculated enhancement, one would expect a larger fraction of this D0 D bar 0 tech jet in heavy ion collisions. And so we did this Pussier study with just NTKT jets declustered with fast jet, I think usual radius, and with a simplification, we didn't deal with multiple D0s or multiple anti-D0s, because then you have difficulties to trace back the charm current inside of your jet. And we considered only prompt D0 contributions. With this, you get a sizable number of events with assumed luminosity of run 3 for Alice. But this is not the only experimental strategy. So one could think, instead of going to the D0s, one could think of muon tagging and do some semi-leptonic charm decays to trace back the gluon to CC bar sample. Yeah, so the measurement is proposed for the Alice upgrade, and we were now thinking how to embed the parton in the parton shower the medium modification, and the ideal strategy would be to have the modified splitting function, but of course this is not, you cannot hack QCR directly to put your new splitting function. Nestor has ways to do it with QPCR, but so we worked out a simplified procedure who conserves probabilities, and we reweight each splitting to account for the modified gluon to CC bar probability with this simple formula where each splitting may have more inside and is then divided by the vacuum. So this captures already qualitative features of in medium modification, and here I'm showing you this QCR output. So you have the ratio of this D0 anti-D0 tagged jets over all inclusive jets, and as you expect with rising jet PT, you get more because the gluon has they're more higher energetic gluons, so you get more splittings. Then we use this counting experiments and correct with jet quenching. We do just a simple shift in PT, both for the tagged and inclusive jets to establish a baseline. And using the aforementioned probability modification, we get out this red band where one sees the enhancement of this D0 anti-D0 jets compared to the vacuum baseline QCR PP. On the box, you see that it's around a 30% modification, and this magnitude depends on of course on the observers. It didn't shift much depending to our discussion we previously had on the splitting function. So this is based on the corrected and generalized one. Allow me to conclude. I've shown you gluon to CC bar in medium production of heavy quarks, the splitting function with BDMPS modification. One sees the broadening of CC bar best and enhancement of CC bar radiation. And we devised the experimental observer where we can see this enhancement. Of course, we are working on the formation time observable and on the different distributions coming out, the D0 and anti-D0 distribution, and gluon virtuality concerning this splitting function. So thank you very much for your attention.
Thank you very much. So do we have questions? Sorry, let me stop the recording.